All right, so time's up. Let's go ahead and get started. Good morning, everyone. I hope you all had a nice long weekend after another long weekend. Now we are going to be in the thick of it for a pretty long time. And so expect those 5-day school weeks every week. Mentally prepare yourself for that. Make sure you're getting good sleep each night. What we are going to be doing this week is we are doing a set of lessons. We're going to be working through the rest of completing and balancing equations this week. And we're also going to learn how to determine if any compound that's ionic is completely soluble in water or is classified as only slightly soluble in water. We'll be doing that on Friday. Just to look at the schedule, I have it posted up on the board. You'll see there's a Unit 5 quiz posted and a Unit 5 lab posted. Both of those are for next week. So next week for our class, it'll be Tuesday. We're going to have a lab on Tuesday of next week. And that's going to be to go over all of the types of reactions we've been learning in class. So you'll have that more or less full class lab, second half of class on next week, Tuesday. And then next week on Thursday, we'll have a quiz on the first half of the unit. And so that means that it's going to be about every 2 weeks, half of unit, full unit, half of unit, full unit. And so we're going to be at our next quiz once again next week on Thursday. And remember, quizzes are small grades, but they are a checkpoint to see if you're understanding what we've done so far. And so let's go ahead and get started with that second lesson. I'll go ahead and get the drawer very shortly. But I do want you to go ahead and write the lesson title down while you're waiting for us to get started. It is Unit 5, Lesson 2. What we're going to be learning how to do today, and we have to spend a whole class period on it because it is more complicated, is how to complete single. You already tested?
Yep.
Okay. So just go ahead and jump in and get ready with everybody else. Unit 5, Lesson 2, completing single replacement reactions. And this is technically completing reactions part 2. You'll notice that there's a paper that I passed out to you. There is good news. The good news is that you do not have to memorize that paper. I will be providing that to you on your next quiz and your next test. The bad news, I guess, is that you're going to have to understand how to use it to be able to predict what metals are more reactive than others. And like all the types of reactions, you're going to be given the reactants, and you're going to have to figure out what are the products. What is a single replacement reaction? We'll go over how to complete and balance it, and then we'll take a look at some important single replacement reactions. I'm giving a little bit of time for you to write the title. We're about to get started shortly. I know that there's a couple students who just got here, so I'm giving you a minute to go ahead and get the title, and then we're about to get started. The good news is that for most of these reactions, the wording gives away what's happening. The word replacement means something. What does replacement mean? If I have to replace, it's like a substitution. And so we can already see without learning anything in the lesson that some kind of switch is going to occur in this type of reaction. And the word single means one switch. So one switch is going to occur. So we're going to go ahead and take a look at the type of reaction, what exactly is going on, and then how to predict the products, their states of matter, and that whole process that I taught you last class. So you'll want a periodic table with you every class period this unit, because you are going to, every time you make a compound and it's ionic, you're going to need to use the charges to come up with the correct amounts. So either you have a periodic table that's the laminated one that you've memorized the charges on, or you have one that's written that you can reflect back to as we go through questions. But this periodic table, you should have one that's written that has the 7 on it, it has P4, it has S8, and then it has all of your charges, +1, +2, +3, -1, -2, -3 for group 17, 16, and 15. We're going to be, I'm just going to write on it again because we're going to come back to this when we are actually doing questions. And then as you can hear, of course, exists as 2 along with hydrogen. And it exists as an element, it exists as H2. All right, so we're going to go ahead and get started. What is a single replacement reaction? You do need to go ahead and write this down. There are 2 versions of this general reaction. A single replacement reaction is a reaction in which one element replaces another element in a compound. And so you've got a compound, and one element gets kicked out for another. We call this a single replacement. Now you're going to see that there's 2 possibilities for general reactions, and we're once again using these letters A, B, and C to represent our different elements or cations and anions. So A, B, C represents elements or polyatomic ions, to be clear. Something with a positive charge, something with a negative charge, and it's in a compound. Did I get picked up? All right, let me see if I can. Works today. If it's being awful, I might ask of you to be closer. Let's give it a go. I was struggling with it about an hour ago. I'll just rewrite what I had then. The part that I circled is the part you need to have down. And then I also added a little bit more here. A, B, and C, these random letters, they either represent elements or polyatomic ions. So then a single replacement reaction, this is one in which one element will replace another element in a compound. And there's going to be 2 types that occur. This reaction that you see on the screen is likely one of the reactions that we're going to do next week. It is the replacement of copper with silver, actually. And so what you see forming on top of a copper wire here is you see silver forming at the top. Some of you may ask, is that real silver? And the answer is yes, it will be real silver. The reaction is, you'll of course be doing a small amount in a test tube. But each small vial of silver nitrate is about $30. So make sure to write down the general reactions, and what we're going to do is we're going to see when we use each one. How do we know if A is joining with B, or if A is joining with C and kicking out B? How do we know which one's going to happen? Giving more time because I still see some writing, and I'll be moving forward shortly. And I also want to remind you from last class, if you see a single element, for example, you see A here, a single letter, capital letter, that's representing we have a single element, whereas BC is representing that we have a compound when we have two of the capital letters. So the letters A, B, and C are just that we don't know what random elements these are, but if I see a single capital letter, that's going to represent an element, and if I see two capital letters, that's to represent to us that whatever we have going on is a compound. All right, good to go? So how do we know, and we're first going to go here, how do we know what's going to happen if we have the first type or the second type? And so I'm going to go ahead and write the first type here. In a single replacement reaction, if the element that's by itself is a metal, if it's strong enough, then the metal that's in the compound, it'll kick it out. So that's this type. If A is a metal, and you've got this random compound, when we look at a compound, we learned that there's a specific order. Does the metal come first or does the non-metal come first when we write a compound? We're supposed to write it a specific way. Which way?
Metal.
Metal comes first, right? In a compound, you've got a metal or a cation, which is why I wrote it like that, cation. Metal or another cation. And then this is a non-metal. Anion, negative charge. And so in the first type of single replacement reaction, if A, the element that's by itself, is a metal, it's going to look to swap out with either the metal or the cation that's in the ionic compound. And so if the metal that's by itself is stronger than the metal that's in the compound, meaning if A is stronger than B. So A has to be stronger than B for this to happen. Then what will happen is that A takes B's spot in the compound and kicks B out. It replaces B. And so you've got A, C plus B is your result. A takes the spot of B and B gets kicked out. Another way to understand it is something that will become a cation in a compound will replace another cation in a compound if it is strong enough to do so. That's a big if, and that's what the paper I passed you out is to reconcile. How do we know if a metal is going to be stronger than another metal and replace it? The second scenario, which we'll see more towards the end of class today, is if A is a non-metal. So what if A is a non-metal? Then which of the elements in the ionic compound would A be replacing if it is strong enough to? B or C? For the ionic compounds are always written one way. It has to switch with another non-metal. And so this being a metal or a cation, and this being a non-metal, an anion, a non-metal will switch with another non-metal. And so you get the second general formula, which is now C gets kicked out, right? And you have, technically it should be written BA plus. And the swap that's taking place is right here. And a non-metal can only kick another non-metal out if it is stronger once again. So A would have to be stronger than B. And we'll go over how we can make that prediction. I'll give you some time because this is the general outlay of what's going to happen. Before I continue, if this is a metal and a non-metal, or an anion and a cation and an anion, what are we making here, AC? Are we making a ionic compound or a covalent compound, generally speaking? metal and a non-metal, or a cation and an anion, then it must be a ionic compound because it's got ions in it. If it's got ions in it, it's going to be an ionic compound for the most part, with one exception we're going to talk about today. B. What's B? If I see a letter by itself, what does it mean I'm making? Is it a compound or an element? An element, right? So the reason why this type of reaction is going to need so much time for us to go over it, it is the most complicated because you're making both an ionic compound and an element by itself. So you'll need to use both strategies. You will both need to know how to make an ionic compound from its cations and anions using the periodic table, and you're going to have to know the standard states because when elements are made, they're made in their standard form. I'm going to wait a little bit before moving forward. But everything here is important. There's one major class of cations that's technically not a metal, but acts just like a metal that we're going to talk about pretty shortly. Yeah, go ahead, grab the purple pack. So, what element acts like a metal, but actually isn't a metal? Random fun facts that are going to be important. What element acts like a metal, will react as if it were a metal, but it is not a metal? Not silicon.
Mercury. Isn't it the one that will melt?
One even more famous, or some,
Like
no, more famous. Aluminum actually has properties of both metals and non-metals, but it's not the one I'm thinking of.
I forgot this thing, but it melts like in your hands temperature.
Let's go ahead and take a look at the series. So this series describes you, and you'll spot it out shortly. This is called the metal activity series. On the top of it, write Unit 5, Lesson 2. Also write given on quiz/test, meaning I am not asking for you to memorize this, but I am asking for you to be able to utilize it. My strategy, as I've told you many times, is if Cambridge doesn't ask you to memorize something, I'm not going to make you either. When I studied chemistry in university, I actually did have to memorize a list like this, and it was gross. I hated it. Because besides, knowing your general trends, it just seems like a random order. But there is some sense we can make off of it. So let's take a look at the metal activity series. This actually tells us which metals are more reactive and which metals are less reactive. And so take a look at the top. What does it say is the most reactive metal? Potassium. And then the whole first three are where on your periodic table? Group 1. Does that make sense that group 1 metals are highly reactive? They wish to get rid of their electron. From what we learned a long time ago, actually, we learned that group 1 metals are extremely reactive, and halogens are also extremely reactive with them. Yes. I did send out a message that I had found, or I think the cleaner found it and just put it on my desk. You're welcome. All right, so group 1 metals are here. What comes after? What do you see? There is kind of a trend here. After the group 1 metals comes the barium, strontium, calcium, magnesium. Those all look a lot like group 2 metals. They're not as reactive as group 1. They have higher ionization energies, actually, but they are still quite reactive. Then you've got transition metals and other ones that are definitely not as reactive. So once again, do you need to memorize this list? No. But what you do need to understand is that potassium is strong. So what you have to memorize is that this list goes from strongest to weakest. And so what that tells us is if platinum was put into a reaction, it can replace nothing above it. Same with gold and same with silver. Well, this actually ties into the fact that these are all known as precious metals, and they are technically not very chemically reactive. And so that's why they were used for jewelry, is because you wouldn't want to use a metal that's very reactive for jewelry. It will oxidize. It would change color in the air. And that's one way you know if you have fake jewelry, is if the color changes because it's reacting when it shouldn't be, because it should be a very low reactive metal. So if they tell you it's like, silver, but it starts tarnishing very quickly, maybe it's not. So this is a list of all the different metals, except there's one exception here. There's something else that's in this list that's not a metal. What else is in the metal activity series that's not a metal? Hydrogen. So you want to put a star there. That was the question I was asking. What element is like a metal? It acts like a metal, it reacts like a metal, but it's actually not a metal, and that element is hydrogen. Because hydrogen has a +1 charge. When it forms into an ion, it forms a positive charge like a metal, even though it's a non-metal, and this is due to its low electronegativity in comparison to all the non-metals. And some more special things about hydrogen we'll go over in a little bit. And so any element that's actually above hydrogen on this list will kick out hydrogen from a compound. So just to illustrate that real quick, I have some HCl. We'll be talking about this in a little bit. It's called hydrochloric acid. So it's HCl. And then I have some magnesium. This is my little magnesium wire. If I look at magnesium, where's magnesium on the list? It's right here, right? And hydrogen is down here. So according to theory, the magnesium should replace the hydrogen, right? According to theory, let's see. I always test my stuff beforehand, so you might have heard it during the bell work. Does it? If it does, it means a reaction's occurring. Is a reaction occurring here? Yeah. As soon as I put that magnesium in, it started bubbling. And do I see the magnesium wire anymore? Is it there? No, it's completely... Well, where is it? Where's the magnesium? Where did the hydrogen go then? Because it's H2 gas, right? And so that's why in theory, we're going to see in the lab next week, what we're studying in theory, we'll actually see that in practice. But that's just a little demonstration to show that that's what we're doing. We're doing reactions that exist. This all exists. This has been studied. We know that magnesium would replace hydrogen. So if I go in my lab and I'm like, oh, I want to mix these two things together, I can figure out what labs I want to make for you, what's going to work and what's not going to work based on what I know of the metal activity series. And so you'll be predicting, part of what you'll be doing in your next lab is making predictions and figuring out will this work or not, and then testing it. Will that work? And so we know that magnesium replaces hydrogen and kicks hydrogen out. Would potassium kick zinc out of a compound? Yes. Would silver kick iron out of a compound? No, because it's not powerful enough. So the idea is that you're going to be consulting this list to see if the metal that's by itself is going to kick out the metal that's in a compound. That's what you're going to be doing. So hold on to it, keep it, because we're going to use it for questions a little bit later. There's a couple more things. I just added this before class today. A little bit more about hydrogen. First off, when you see hydrogen in compounds, you're usually going to see it as HX, where H is hydrogen and X is some kind of non-metal or polyatomic ion. So you want to add this into your notes. Whenever you see hydrogen in a compound in this unit of study, you're going to see it in the front of a compound, and it's going to be operating like the metal. It's going to have a positive charge like a metal. This is because whenever you have H with a +1 charge in a compound, this is actually the formal definition of acid, what an acid is. And so you're going to want to write that down. We'll be talking more about acids later on, but because we're going to be working with them very soon, I'm already working with them now. They do a lot lot of the reactions, we need to at least have an idea of what an acid is.
What's the strongest?
Well, it depends on more than one factor, but there are extremely strong acids. A lot of people would argue that sulfuric acid of 98% concentration is the strongest.
What would it be like?
It can corrode a lot.
Metal?
Yeah, for sure.
Yielding
Mhm.
people?
The periodic table of videos has a chemist that tested all of that.
Oh my
Oh.
god.
But like
all
with
of them?
not people with chicken legs, just to see if it would eat through flesh.
Oh my god. Oil.
So that does exist on YouTube. Not right now. I do show it because when we learn about hydrofluoric acid, HF is strange acid. That's where that video comes into play because that's the acid that it is. All right, so H plus 1 is considered acid. Whenever it's in a compound, you've got H with a +1 charge, that is defined as acid. It's interesting to note something. H plus 1 is actually quite fascinating. I want to bring it up. Notice I put the 2 1s there. Hey, what is that? What did I just do? I just put a 1 on the top and a 1 on the bottom. Pull back to the recesses of your brain. What did I just fill in? I filled in the mass and I filled in the atomic number. Acid actually, which is H plus 1, has how many protons? Neutrons and electrons. The other way. Every element has to have a proton because that's the definition of what makes an element an element. No proton, no element. So it's 1 proton because the atomic number is 1. And then you're supposed to do 1 minus 1 to get the neutrons because the mass number is the combination of your protons and neutrons. So you have no neutrons. Because, and 0 electrons because the one has been taken away, right? Literally, an acid is a single rogue proton running around and causing havoc, to be honest. That's what an acid is, it's a single rogue proton. And so any solution that has an acid in it, if you were to read advanced science materials, they would call it a protic solution. An acidic solution is known as a protic solution. And Cambridge does use that terminology. And the reason why they call it protic is because it's literally just a proton. It's just single protons. And so acid can also be called a protic solution. But anyways, the idea that I just want you to have now is that you see, if I see a compound, I see H in the front, that H is going to be an acid and it always has a +1 charge. Can hydrogen have another charge besides +1? Can it have any other ionic charge? Yes or no, and why? It could be if put with something that's way less electronegative than. So in very, very unusual circumstances, it could be -1. Could it be in the front of a compound and have anything else than +1 as a cation? Can it have another cation charge? Can hydrogen ever be +2? No. Can hydrogen be +3? You could only take away 1 electron, right? So be careful with that when we get to practice questions. It says protic, like proton, it's called a protic solution if you have acid solution. The fancy terminology is protic. Without acid, it's called aprotic, actually, because A means without. That's just terminology you may see or read in passing at some point. All right, so I'm going to ask you to go ahead and do this. I'm not asking you to memorize a whole list that you have seen before, but I am going to go ahead and ask you to do this by the end of the unit of study. So by the end of the unit 5, you need to have your basic acids memorized. These are the acids that are used every day. And we'll have a lesson on acids later on, but just so that you have the list of the most common ones that you're going to see here and there, including in next week's lab, go ahead and write these down. Whenever we see H2SO4, that's sulfuric acid. Notice the S is there, that's sulfur. That's where the name is coming in. There's actually a trick with your polyatomic ions, if you memorize them. If you just look at the polyatomic ion, you would change the ending of the name to and acid, meaning nitrate becomes nitric acid, carbonate becomes carbonic acid, phosphate becomes phosphoric acid. So every single one of the acids ends in ic that you are responsible for knowing. And then HCl becomes hydrochloric acid. That's the only one that has hydro in the front because it's only got two elements. It doesn't have a polyatomic. With the polyatomic, they don't put hydro in the front. But if you know your polyatomic ions, it's just switching the 8 for ic acid. So there's sulfuric acid, nitric acid, hydrochloric acid, carbonic acid, and phosphoric acid. These are a selection of acids, the ones that are most common. A long time ago, I gave you a video on Edpuzzle, and it had all the naming strategies for acids, if I recall. Like it went over us acids and hypo-us acids and per-ic acids, and everybody was freaking out about it. And I told you not to worry about it, and that's because Cambridge doesn't make you memorize a lot of acids. They only want you to know the main ones. Sulfuric acid, just for fun facts while I'm waiting for you to finish writing. Sulfuric acid is used as battery acid. That's what it's mainly known as. Like the car battery acid that we use is with sulfuric acid. That's why they tell you if you're changing a battery in a car to be very careful because you don't want that acid to spray. You could actually, really injure yourself, get permanent skin damage for that. It is a mediator because it's part of a redox reaction, which is what we're going to talk about later on in this unit. It serves as a mediator and a transfer of electrons, which will cause electricity. Right? So it helps the car. It can, yeah. That's why I said it'll leave permanent skin damage, depending on how much gets on your skin and how long you let it sit there without neutralizing it.
Does acid do like burn?
That's what it will feel like. It's called a chemical burn, but yes. That's what they call a chemical burn. It's not a fire burn, it's a chemical burn, but it still gives skin, like big skin issues. You have to get skin grafts if it's really strong.
So all of these are
Depends on concentration. Something you learn about in the math part of the class. So depending on concentration, some of them are definitely more strong than others, which we're going to learn about as well. Nitric acid is one of the components, along with sulfuric acid, is another component of acid rain. If you've ever heard of acid rain, what can corrode your buildings from being produced in industry, acid rain is when you have extra sulfuric acid and nitric acid in your water that's in your rain.
But what does it do to your skin? What is what makes it like fire burn?
It's corroding your skin, just the same way that it did to that metal. If you think about it, it's saying how does acid corrode your teeth? So it all goes into that. And so hydrochloric acid, this is the acid that's in your stomach. So the acid that's in your stomach that is dissolving food on a regular basis, what we call our stomach acid, is actually hydrochloric acid. We also call it muriatic acid because it's used as pool cleaner. If you've ever had a pool or had a pool cleaned, people will use muriatic acid, which is hydrochloric acid, to clean it, to provide that source of chlorine, which is a disinfectant for the pool to get rid of like bacteria and stuff. Carbonic acid is extremely important because that is in your blood to maintain the pH of your blood a certain level, and also in the sea. Like by sea, I mean like the ocean, to make sure that the pH is around where it needs to be for your animals and wildlife to survive. And so acid rain can actually also lead to having too much acid in it as well, like in your rivers and streams. And then finally, phosphoric acid. The main place that I think that I remember phosphoric acid is if you ever drink Coca-Cola, which I stopped drinking a long time ago, and you read the ingredients list, phosphoric acid is there actually. So just random fun facts about acids. We'll have a whole lesson dedicated to them, but at least you have an idea of what they look like moving forward. And so when you have a lab now next week and you see H in the front, you're going to be like, oh, that's an acid. I know what that does. Gloves and goggles. So at the very minimum, you know to be careful at this point. All right, so the first type of question we're actually going to see. Determine if each of the following reactions will occur or not. So go ahead and write them down in your notes. Consult your list that you are provided, the metal activity series, and tell me if these reactions happen or not. It's a yes or no. Through a process called hydrolysis. It breaks the ester bonds down. It basically breaks down your macromolecules into smaller macromolecules. Like, you know how you have polysaccharides and you have amino acids that are very long? It breaks them into their little parts so that when they go through the rest of your body can put them where they need to be.
No, she's saying why doesn't it run through your stomach?
It depends on the concentration. But
No.
Why your stomach?
oh, okay. I did. It doesn't burn through your stomach because you've got protective like barriers in your stomach, and you've got like, I would say it like phlegm and stuff that serves as protective barriers. But actually, acid reflux is a condition that people have, that the stomach acid escapes into their esophagus and then causes ulcers over time. It's called acid reflux. All right, so it's interesting because acids is actually one of my favorite topics. It's a very interesting topic. So let's take a look at each one. And then take a look at the first one. The question is a yes or no question. Will each of these happen? What do we have to check to know if it happens or not? What is the comparison we have to make? If this is a metal, which it is, then it's looking to replace what in the compound? What is it trying to replace? Sodium. And so I'm just going to circle that. So magnesium would have to be stronger than sodium for this to happen. Well, take a look at your list. Is magnesium stronger than sodium?
It is
Not. So if it's not, the answer is no. This is not happening. That is not happening. And the good news is that if a reaction's not happening, you don't have to complete and balance it because it's not happening. That didn't happen. So no reaction can be an option on your next quiz and on your future quizzes, future bell works. So this is no, which means no reaction occurred, which to us will mean boring. We mix the two things together and it just sits there like dropping a rock into water. How exciting. B. Will this happen? Cobalt versus tin, right? Cobalt versus tin. Is cobalt stronger than tin? Take a look. Is cobalt stronger than tin? If it is above tin, then it is stronger than tin. So, yes, reaction will occur. Yes, reaction. All right, the third one. I should talk about this a little bit more back to our list right here. Take a look, there's something on the side here.
Yeah.
This says these elements from potassium through calcium are so strong they will react with plain old water. Magnesium through lead are strong enough to react with water and with acids. That means with these, with H in the front. So you may want to fill that in, that they react with acids. And reacts with water means reacts with what in the water? The hydrogen in the water. And so when it says reacts with water, that means reacts with the H plus in the water. So you may want to fill that in for water. Underwater, water can be rewritten as two ions, the H plus ion and the OH minus ion. These are the two components of water actually. And what makes water neutral? Because H plus is acid, and I haven't taught you this yet, but OH minus hydroxide is actually base. That's actually the definition of base. And so water has equal amounts of water and base in it, which is why it's completely neutral. It's distilled. And so these metals are so strong, they'll react with water. These metals are strong enough to react with acid, but not water. And these metals are weak and will react with neither acid or water, the ones that are at the bottom. And so going back to the practice questions we were looking at, is magnesium strong enough? Didn't I just do that? Magnesium with hydrochloric acid. That was the one that I showed. Did that happen? Was magnesium strong enough to kick out the hydrogen?
Yep.
Yes. And, oh, I asked, where did the magnesium go? Where'd it go? It's dissolved in water, right? The magnesium is in the solution. So it went into the solution, and what came out of the solution was the hydrogen gas, right? Which we observed as it looked like it was steam, but it was actually H2 gas coming out. So yeah, this is going to happen. Yes. And then this one, Fe plus SrOH2. Iron versus strontium. Take a look at your list. Remember, you're allowed to use that. You're going to have a copy of that on your next quiz and your next test. Is iron strong enough to replace strontium? Yes or no? Iron is weaker than strontium, right? Because it's below it on the list. And so the answer is no. Reaction doesn't happen. Meaning you don't make these products. You don't make anything. You just have what you had to begin with. See me crossing it out. It's just no reaction. It doesn't happen. All right, so you will be asked to predict whether or not the reaction happens. The second thing you're going to be asked to do is if the reaction happens, you're going to have to complete it, balance it, and give the states of matter, like we did for the other three types of reactions. Now you can see why we probably are taking a whole class period just for the one type, whereas last class period we went over 3 types. So there's more to this type. So we're about ready to get started. If you need to remind yourself how to complete and balance, remember I gave that sheet out last class, how to complete and balance any reaction. That is the last part of what we need to do for being able to accurately predict single replacement reactions. So have this sheet out if you need it handy. I'll be going over the steps over and over again. Ready? So complete and balance. The type of question you're going to see. It says determine. So this is the question. Question 1. Or example 1. Determine if each of the following single reactions are going to even happen. If it does, complete and balance the chemical reaction, giving the correct formulas for your reactants and your products. And so following the method that we learned last class, only once we predict that it's going to happen, then we'll start working through these steps. So my first question is, does this happen? Before we even start working through the steps.
No.
Does it happen?
We don't do the
I'll give some time for you to write it down. And we'll address it. Is magnesium stronger than, and what it would be?
It's not stronger. Oh, you
Magnesium is right above it, just a little stronger, right? So your template is A plus BC, right? That's your template. What would A be kicking out if this reaction happens? B. So if A is kicking out B, then what you should be getting as a result is A gets together with C and B gets kicked out, right? That's the single replacement that is happening in this type. This is the type. Because it's metal or cation replaces metal. it happen? Yes. Why? Because magnesium is above aluminum. We have to address this because that's where confusion occurs. Is why does it happen? How does it happen? So once we predict that it happens, well, now you have enough, you've learned enough in this class to predict what the products are. You can tell what the products are, and how can we tell that? Well, what are we going to be putting together? So step one, in complete and balance. What is AC? What are we putting together?
AC is
We're putting together magnesium and nitrate. So step one was to get the element and get its charge. What is the charge of magnesium? If we're in a compound, we have to get the ionic charges. What is the charge of magnesium? +2. Okay. This you're going to want to pay attention to. You're going to notice I took off the polyatomic ions from the front of the classroom. I'm not giving you those for this unit. You're not going to have them to consult. Because you can look at the reactants to predict what the charge of that polyatomic ion is. What is it? Crisscross. Right? Reverse crisscross. Aluminum would be +3 and nitrate would be, that's an invisible 1, so it has to be -1. I expect you to be able to do this, to get the charge of the polyatomic ion because it is provided to you in the compound on the reactant side. So the charge of nitrate is NO3 -1. The charge of a polyatomic ion never changes. Nitrate is always -1. If you don't want to do the reverse crisscross strategy to get the charges, then you're just going to have to rememorize the polyatomic ions, the same 12 that I gave you before, because those are the ones we're going to use. But I highly suggest using the strategy here to come up with what the charges are. So now I have A and C, and I need to combine them together. What does this make? What is the correct formula for magnesium with nitrate? Put parentheses around this, and you get Mg1NO3. How many? The 2 comes down. How many nitrates will you have? Good. This is what we learned back in Unit 3. How to put an ionic compound together. And if you forgot that, remember to come to tutoring. So that's AC. Do not just take these amounts and throw them over. Remember that's changing your amounts and fixing your amounts, that's step 2. Step 1 is getting the right compound formulas. Magnesium and nitrate can only combine in one way. You have to get the right way they combine. All right, what's B here? Follow our template. What got kicked out? Aluminum. Okay, so how does that exist? How do we get B? Nope. B is an element. So how does aluminum naturally exist? Nope. That is not how aluminum naturally exists. Aluminium, B, is not in a compound. How does it naturally exist? This is an ionic compound. AC, B is an element. It has elements by themselves have no charge. Elements by themselves have no charge. I'm going to repeat that again. Elements only have charges when in compounds. This is a big mistake that can happen. Elements by themselves do not have charges. They just exist in their standard state, which means aluminum just exists as 1, right? Because all metals are monatomic. So you can see where it's getting complicated. Because everything we learned, you have to remember. So that was step 1 in here. To complete the reaction, we had to make the correct formula for the ionic compound and the correct formula for the element that's being kicked out. What's step 2 in this process of completing and balancing? The next step is to balance the equation. I don't see underlines. What do we got to do? We got to make them ourselves. right? So we fill in the underline. So now nitrate, I see 2 and 3. I want to make those A. Nitrate, there's 3 here and there's 2 here. So the first number in common is 6. So I'm going to put a 3 here and a 2 here. Fix your aluminiums to 2. Fix your magnesiums to 3. And it is balanced. Step 2 is done. Step 2, balance the equation. This is the same steps from last time. Every time you complete and balance, follow the same steps. Finally, what's the last thing? The process. Every time you complete and balance, you start with making the right formulas, then you balance the equation. The last step is states of matter. So states of matter. Magnesium nitrate is an ionic compound. Is it in water? Yes or no? Take a look at the reactant.
No, it's not in water.
Totally is. You look at this process. You took magnesium and you threw it in an aqueous solution, right? This is an aqueous solution. This is literally saying I dropped magnesium in here. I took a solid, I put it in an aqueous solution. Any ionic compound, and I'm just gonna put a star here, in case it's hard to remember otherwise. Any ionic compound in a single replacement reaction is gonna be AQ, because it's in water. It starts in water, it ends in water. In single replacement is AQ. And you know that because if it starts aqueous, then it ends aqueous. And what would the state of matter for aluminium? The metal. It's a solid. That's it. I'll pause to give you time to write that note and finish the question. And then we're going to do, of course, more examples. You've got to get the hang of what to do here. So you've got to know standard states. You've got to know how to put ionic compounds together from the ions. The new thing is memorizing the template, like what type you have, and being able to consult the chart to see if a metal replaces another metal. Ready to see another? I'm going to move forward about 25 minutes. Just those we're wrapping up a little bit of time. So let's try these with let's try these with acids. Determine if each of the following single replacement reactions occur. If they do, complete and balance the chemical reaction given the correct formulas for reactants and products. It's cadmium. Yeah, go ahead. Is cadmium stronger? Take a look. Is cadmium stronger or strong enough to replace what in H2SO4? What would we be looking at? What are we comparing? Cadmium versus
Sodium. But no,
sodium here.
I mean, that's all.
Cadmium versus H, right? Because this is a metal. Metals and compounds would have positive charges. It would replace a cation. Hydrogen is a cation. So look at your list. Look at the paper. Is cadmium going to replace hydrogen in sulfuric acid? It will if it's above it.
Oh,
This is H plus 1 right here. Will that happen? Yes. So it happens. So the first question, does it happen? Yes. Well, now we got to make it happen. What does that mean? What is the template? Well, first you gotta know that you're doing this, right? Cadmium is taking hydrogen's place in the compound. That's what's happening. Cadmium is kicking that hydrogen to the side, out. Cadmium's going in. So how does that happen? Step 1. If I know my template is, once again, it's going to be A plus B, C, and then A gets together with C without B, right? That's the template. Then what I have to figure out is what is the compound I've made here between A and C. So you should identify what is your A and what is your C to figure this out. What is your A? In the reaction. What is the identity of A? Cadmium, right? Cz. What is the charge of cadmium? I think we went over it last class. Just in case. Let's go back to that periodic table. Did you remember there were 3 elements you were supposed to just straight up memorize their charges for? What were those elements? Silver, zinc, and cadmium. What's the charge of cadmium? +2. So in the compound it is always +2. So in this compound we're making, cadmium is 2. And what is C here? What is C? What is the identity of C? It goes with B plus C minus.
Oh, that's
What is C?
SO.
It's sulfate. Right? It's sulfate. Okay, sulfate is SO4 with what charge? How will we know? How will we figure that out? You're not going to have a list of polyatomic ions. You can figure it out. What is the charge of sulfate? Is the amount of hydrogen to predict the charge of sulfate. The charge of sulfate is, this is nothing different than what we did back in Unit 3. It's called the reverse crisscross technique. We did this. The first element's positive, the second element's negative. No? We did this before. Sulfate is -2. It is always -2. It is never anything different than -2. That's what sulfate is. I'm just saying you can actually predict it from the reactants. You can figure out what it is. You don't have to rememorize the polyatomic ions if you understand that technique, which is why they're being taken away from you. Because technically, you would have to do that on if you were to take it. You have to be able to figure that out. And this is even the high school level, you need to be able to figure it out. All right. So now what do? To put A and C together? Cadmium has a +2. Sulfate has a -2. Do those charges cancel?
Yes.
Cancel them, and you write the correct formula, which is CdSO4. That's AC. All right, what's B? What got kicked out? How does hydrogen get kicked out? In its standard state, which happens to be H2. H2 because it's its standard state, not because it's H2 here. To be clear. Oh, so that's step 1.
Yes.
What's step 2?
Balance.
Do I have to do anything to them? You should note that this is already balanced, right? And then step 3, states of matter. Cadmium sulfate, ionic compound, in a single replacement reaction. It starts in water, it ends in water, so it's aqueous. And H2, what's the state of matter of that? And you would just see like bubbling out. That's how you know that you were making a gas. Gases bubble out of the mixture. All right, are we starting to kind of get the hang of it?
Yeah.
Take a look at one more with an acid. Oh, and then we got water going on. All right, aluminum plus HCl. Is aluminum strong enough to replace hydrogen? So I'm going to go ahead and just erase what I have on the side here. And I'm going to ask for the second one. Does it happen? Does the second reaction happen? Yay or nay? Does the second reaction happen? Al and H.
Yeah.
Aluminum is higher than hydrogen. It says aluminum reacts with acids on the chart. On the chart. So that means we got to do the reaction. It's the same type. Metal is replacing a cation, so we're looking to make the same thing. Aluminum's taking out what?
Taking out hydrogen.
So step one. What is AC this time? What is your compound you're forming? What is it between?
ALC.
And you can just line up the template here, right underneath, just to make sure that you know what part is what in. As soon as Sarah comes back, you'd be next. AC plus B. I'm writing this over here to make my compound correctly. What is my identity of A?
A is AL.
And it's being put together with what? CL. You have to put them together correctly. ALCL is not correct. How do I put these elements together in a compound correctly? I have to get the charge of aluminium, which is group 13 is, and I have to get the charge of chlorine. What is its charge? -1. Perfect. Now what? Same strategy. Swap. So you get AL, CL3. That goes where you put AC. AL, CL3. What is my other product? I made my AC, now I've got to make my B. What got kicked out? Hydrogen. How does hydrogen get kicked out? H2. You have to provide the standard state. When hydrogen gets kicked out, it gets kicked out as H2 every time. Step 1 done. Step 2, balance the equation. To go back to a little bit. I'm just going to tell you that this is a 6 in front of here. This is a 3, this is a 2, and that's a 2. You can work the balancing back and forth. We went over that a couple weeks ago. It would be 2, 6, 2, 3. Balance that one.
Did you really know before?
Well, the thing is that I did do it in my head a little bit because the idea is that you have to change the hydrogen. You can change it to a 2 next to the hydrogen. You now have 2 chlorines and 3 chlorines, so you have to make 2 and 3 equals 6. So then you have to go back and change the hydrogens again. So I understand it will take more time. You don't have to do that fast, but that is the step, yes. You can be next, yes. All right, so that was step 2. What's step 3? States of matter. Your ionic compound is always going to be AQ, and H2 is its standard state, which is? Okay, that's it. All right, we're going to take a look at what happens with water. What happens with water? This is super important because we're going to be doing a lot of reactions, and sometimes water actually reacts. Sometimes water, which is usually the solvent, will actually react. I'm pausing just a little bit for those who are still working on this to finish, and then we're going to go through the next one. So you can definitely see where this is starting to get more complicated because you have to follow through a lot of what we learned how to do earlier this year, all in one question. All right, ready to look at water. Take a look. First thing, so I'm going to write here reactions with water. Since I didn't give the title. Whenever you see water in a chemical reaction, it would serve you well to rewrite water in the following way. H plus 1, OH minus 1. Because if water reacts, the cation in water will be H plus 1. And if water reacts, I said if, the anion in water will be OH minus. This is water. There's 2 hydrogens and 1 oxygen. So if water is broken up in a chemical reaction, this is actually what occurs. OH takes 1 electron away from one of the hydrogens. So if water reacts, that's how it's going to react. Will water react with aluminium? Take a look. Aluminium reacts with oxygen. will not react with water. Only calcium and above react with water. Meaning that aluminium, which hopefully that makes sense. You can go home and put water on aluminum foil, see if it reacts. But, you know, that's why they use it to close containers and keep your cans fresh, because it's not gonna react. Aluminium's not strong enough to react with water. There's also an oxidative layer on it, but even without it, aluminium will not react with water. Yeah, we're gonna have to agitate that when we do a reaction with redox, which is not too far away. It's in the second half of this unit. We're doing redox in a few weeks. So aluminium is not strong enough, to be clear, to react with water. Meaning, aluminium is not stronger than hydrogen. This will not happen. If it doesn't happen, what's our answer? No or no reaction. NR is what people typically write for no reaction. No. Which depending, probably wouldn't put that in a Cambridge exam and just put no reaction, because if you put NO, couldn't that be Nobelium? Like, I don't know, like. You know,
Even know Nobelium would
it is. Go look for it. It is an element, so it is no reaction. It's not gonna happen. Hey, wait, does that mean you're gonna have questions in the quiz that are no reaction? You don't have to complete and balance them, and you can figure out they don't happen?
Yeah. That's like.
If you can figure it out that it's not gonna happen, then you don't have to do all that work, right? What about the second one? Does that one happen?
Yeah.
I have to show you one where it happens, don't I? So this happens, yes. I have to. Or else when you get your own questions, tell me something. You'll be confused and then you'll all ask me. And then I don't think so. Actually, I expected there's a professor that would totally do that. I've had professors like that. So this happens. You have to understand that when you see water, you're going to see it as H plus and OH minus. You should write that underneath. Like as it's H2 liquid, you write it as H plus and OH minus. Because what is sodium replacing in water? It's going to kick out the hydrogen and it's going to take its place. How does sodium take hydrogen's place? So how do we put together A with C? So back to step one again. What is the charge of A? A is sodium. Plus 1. What is the charge of B? And OH minus. It's OH minus. It's not just oxygen. That's why I said you have to rewrite it as this. Because this is what's going to be made. OH minus. Okay. Do those charges cancel?
Yes.
So NaOH. And what got kicked out? And when H gets kicked out, it gets kicked out as H2. You have to remember that. It's diatonic. You've seen hydrogen a lot. Remember that it's H2. Now, what are my other parts? What do I have to do next? Balance. Is this balanced?
Yeah.
I gotta put a 2 here. That'll balance. And then a 2 here. And then a 2 here, I believe.
And then right through here.
Not in front of H2. 2 hydrogens plus 2 hydrogens is 4. 2 and 2. 2 oxygens, 2 oxygens. That's it. This is one of your homework examples, I think, from before with the balancing. All right. Step 3, what?
Elements. They follow the
Sodium hydroxide. It's in water. We literally put this in water. Aqueous. If we put something in water, it's aqueous. Right? Hydrogen is gas. All your ionic compounds are going to be in water. They're going to be aqueous. They're going to be dissolved in water for this type of reaction. This reaction always happens in water, actually. All right, so that's what happens with reactions in water. We have one more thing.
acids.
We did not discuss. No, we discussed acid. We discussed water.
When it's highly unreactive.
We discussed metals replacing metals, but what have we not discussed yet? And at the beginning of the lesson, I told you that metals replace metals and non-metals replace non-metals. So you're gonna wanna write this down. You're gonna wanna write this down. And I am not giving you this on the test. You have to memorize this order.
Oh.
What does that mean? In direct order, fluorine is stronger than chlorine, which is stronger than bromine, which is stronger than iodine. Why would I not give you this on a test? The order on the periodic table is also something we've highly learned before, which is the electronegativity series. Like fluorine is most powerful. Of course, it takes electron from anything, right? So fluorine is most powerful, and iodine is weakest. This is in line with electronegativity. So I'm just going to put the elements in their standard states here because this is how, that's why you see it like this here. Because that's how they'll be shown to you because they're always going to start off in their standard state. So if I have a non-metal, to be clear, you are only going to be tested, even with Cambridge, they only expect you to know the non-metal activity series for halogens. Meaning, will a halogen replace another halogen? So group 17 only. And you can clearly figure it out by looking at electronegativity. The most electronegative element is stronger than everything else and will kick anything else out of a compound. So before we go, we're just going to take a look at an example of two of this just so you can see how would these questions look. So you'll be prepared to do the classwork / homework after this. Because you'll have seen everything. All right, pausing about 20 more seconds and we're about to move forward. Ready? All right, so complete and balance the following reactions or write NR, that's what we standardly write, if the reaction just does not happen. So let's take a look at A. I'm going to give you some time to write down one at a time. So it's complete and balance is the instruction, it's always the same instruction, but you do have the option of no reaction if the reaction doesn't happen. Just to look at the type, what we're looking at here is A plus BC, but because A is a non-metal, A would be looking to replace what?
Yeah, it's non-reaction.
What's the type here? A is a non-metal. What would A kick out if the reaction happened? So it's going to be technically BA plus C gets kicked out, right?
Yeah.
If the reaction happens. So with reaction A, what are we comparing? Bromine versus?
Which is CO.
So bromine kicks chlorine out. Is bromine stronger than chlorine? Bromine is weaker. I'm just going to write that here. Bromine is weaker because it's less electronegative. It's lower on the periodic table is another way of saying that. So the answer here is just or your no. No. Does not happen. No reaction. Nobelium. Obviously, in the previous class, I won't be that stingy. I know what you're talking about. I will give you that answer. Correct.
Just a giant no.
If you put a giant O, like with an N and a capital O,
Like just
recognize that that's nitrogen monoxide now.
Just a cartoon.
All right, F2 plus MgCl2.
Yes.
Does this one happen?
Yes.
Is fluorine stronger than chlorine?
Yes.
Sure. Fluorine is most strong. It will replace anything, right? So then, if the reaction happens, well, now we start in our step. What's the compound we made? It's B with A, right?
Yeah.
So if this is A plus BC, and I usually just write it underneath just to make sure that we're lining them up correctly. What is B? That's going to go first. Mg. And we're putting that together with what? Chlorine. And how do we put them together correctly?
You need to find your
Charges.
Yeah.
you just look the numbers on the side and you don't consider the charges, if you forget to consider the charges, you may get the answer correct sometimes if you're lucky, but like in this one, it would actually work out, but it won't always work out. Be careful. Magnesium is plus 2. Fluorine is minus 1. You crisscross like this. You get MgF2, right? So that's my one product, the Ba. And what's the other product?
CL.
Cl, and how does it exist? No, how does chlorine exist as an element?
Oh.
Cl2, and it's a gas. And you're supposed to memorize that. Which is the last part, which is base.
And I didn't know they took gases.
Gaseous chlorine would come out of this reaction. Gaseous chlorine is actually hazardous if this reaction were to be done. And then what is the state of MgF2? Aqueous. All ionic compounds in single replacement reactions are aqueous because they're all taking some water. Last one. We're taking some chlorine, we're bubbling it into Ki. Does this happen?
Yeah.
Is chlorine stronger than iodine?
100%.
Chlorine is stronger than iodine, which means it will kick iodine. And so, using our strategy, A plus B, C, we're putting together, I'm going to put it together as BA. We usually write it AB, just to put the letters in order, but it's actually BA, because it's metal, then it's non-metal always. So, what would my first product be here? We're putting together B with A. Welcome back. What elements are we putting together to form BA? Go ahead. So step one here is to figure out what is BA. What is B? Line them up. And what is A? Chlorine. So we're putting together potassium as an element with chlorine. Notice I'm taking the element, I'm not taking the 2. Why am I not putting the 2 here? So it's not the charge. That's exactly why. And we do not take over the subscripts because we no longer have an element by itself. It's in a compound. It's going to be a different amount. It's going to be a different ratio potentially. We have to figure it out. What is the amount? K is plus 1.
And CL is
Minus 1. Those charges cancel.
Yep.
The correct compound formula here is KCl. So if you were just to write KCl2, would you be totally wrong?
Yes.
You would be totally wrong. You will be defying. You broke the law. You broke the law again. Octet rule law broken. All right. Next one. C. What is C here? So we got KCl for BA, but what's C? What's my other product?
C.
It's iodine, right? Iodine? The last part, that's the C. So what's iodine when it exists by itself? It's part of the 7, and it is solid. Finally, what's the state of matter for KCl? Now, for both of these, don't we have to balance them? I forgot to balance them. So, it's actually, it is balanced. I forgot to say that. The first one's already balanced. What about this one? Is this one already balanced? So I got 2 iodines here, so I gotta put a 2 here. What else do I now have 2 of? So I put a 2 here. That's it. It's done. For the most part, balancing is not crazy, but you have to know how to balance. All right, so it's your turn. You've got a little bit of time. Start working through the questions. I do have classwork/homework for you. For those of you that are, of course, in here in class, it's going to be due at the beginning of the next class period. I do not assume that you can get everything done, and I don't want you to rush. I want you to actively try to make sure that you can solve the questions, and then if you have questions, you ask me. It's due at the beginning of next class. You can expect next class the bell work to be on this, along with what we've done so far.
What's the date?
Sorry?
What's the date?
The date is the 22nd. Today's the 22nd of January.
It's already got it.
Oh yeah, you did go. Here you go. Here you go. Remember to check first to see that there is a reaction. If there is not, just write NR.